Meow. 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 Hi, Hazel. Oh, you're such a sweetheart. Good morning. You're such a sweetheart, Hazel. What do you do? What do you do? Come here. What do you do? Come here. Thank you. What to do? What to do? Oh, thank you. What to do? What to do? You silly girl. What you do, silly girl? Look at the camera. What you do? Why you not look at the camera? What you do? What you do? Okay, bye-bye. What you do? Hazel's really funny because she sleeps. Actually, both the dogs sleep on the bed with me, and Hazel gets cold at night, so I put a blanket over the top of her, and then every single night she gets out from underneath the blanket and then gets cold and starts trembling. And so the bed is vibrating because of Hazel's trembles. And then it wakes me up, and then I cover her again. And then she gets too hot, she gets out, she gets cold, she starts trembling. I wake up, and this happens like 3 times per night. It's annoying. Why you do that to me? Why you do? Why you do that? Why you do? Okay, bye-bye. Bye-bye. Go away. I gotta teach. What do you do? Oh, okay. She wanna do a fetch. Okay, leave it. I'll show you one fetch. Oh, it's a banana. It's a banana. You want the banana? Okay, you ready? Do. Good girl. You want a banana? Go. Okay, one more. One more. One more. Give me the banana. You want banana throw? Say butter. Okay, go. Good girl. Okay, that's all. Okay, bye-bye. All right, let's go ahead and get started. So, if you can't tell, I have my own language for speaking with Hazel. Actually, I have like a separate language for each dog, kind of. You know, it's like I don't know, does anyone else do that where you have multiple dogs and you have certain things that you say with each dog? But with with Hazel, most of the time I say to her, "What you do?" I say, "What you do?" Or I say, "Where Bubba?" Because ball, she understands ball is Bubba. And she also understands the name of some animals. Let's see if she can. Baby Haze. Lizard. Lizard. Baby Haze. Squirrel. I don't know. I think she's too deaf these days, but she used to respond to those. Okay. So we're going to talk about light waves today, electromagnetic waves, and the speed of light in a vacuum is denoted by c, and its value is 3 times 10 to the 8th meters per second. Okay. If light is traveling through something else, so not empty space, it goes slower than the speed of light, than 3 times 10 to the 8th meters per second. So for example, if light is traveling through glass, while it is in the glass, the light is traveling slower than 3 times 10 to the 8th meters per second. If light is traveling through water, it goes slower. So any transparent material, the light is going to go a different speed. Okay, the atmosphere, the air, light travels slower through the air, but because air is not very dense at all, we will say that the speed of light through atmosphere is basically unchanged because the atmosphere isn't dense enough to really affect. The speed of light is affected by the density of the material that it's traveling through more than anything else because there's more atoms that it's interacting with. You almost want to think about the light like it's a pinball, and if in between encounters with molecules, it travels at the speed of light in a vacuum. But if there's a lot of stuff in the way, it's bouncing into that stuff a lot, and that the bouncing is what slows it down. So we will call the speed of light in a particular medium, I'll just call that V medium. Okay. So there's a thing called the index of refraction. Okay. Which is denoted by N. And the index of refraction is defined as the speed of light in a vacuum divided by the speed of light in the particular medium. So it's a property of the material. So you look up a material, you can look up what its index of refraction is. All right. one thing I want to say about the index of refraction is that the index of refraction actually depends on the wavelength of the light. Okay. So for example, a prism, you might have seen a prism takes white light and then turns it into a rainbow. That has to do with the fact with different wavelengths, which means different colors, travel through the prism at different speeds. And so that separates out the wave. But at this level, we're not going to worry about that effect, so we're just going to assume that each material has just a single index of refraction. In reality, the index of refraction is a function of the wavelength, but we're not going to worry about that. Okay, so if we think about a wave that enters a let's say it goes from a fast medium to a slow medium. So the light, it's a wave, it's coming in like this, and it's going to slow down. Okay, so you can almost think about it like a traffic jam. Okay, in a traffic jam, right, you have, before the traffic jam, the cars are far apart and they're just traveling down the road and there's spacing between them. But once the freeway slows down, all the cars scrunch up and get together. So with the same thing happens with light waves. So it's entering a slow region from a fast region, it's like a traffic jam, and the crests of the wave get squished together. So the wavelength is affected by the speed. Okay, so it might do something like this. And if it goes from a fast region to a faster region, it would spread out. So anyways, I'm going to box that equation because that's important. The wavelength in a particular medium is equal to the wavelength in a vacuum divided by the index of refraction of the medium. Okay, now if we look at the definition of index of refraction, because the velocity of the speed of light in the particular medium is on the denominator, a larger, or sorry, what am I trying to say? Slower speed in the medium results in a larger index of refraction. Okay, so the smaller this number is, because it's on the denominator, we get a bigger and bigger index of refraction. And we can see in this equation here, slower medium is going to increase the denominator, which is going to bring down the wavelength. So the wave is getting squished together. It's a traffic jam. Okay, so the slower the wave goes, the more scrunched up, the more extreme the traffic jam is, and we get a shorter and shorter wavelength. Okay. Important point though, the frequency of a wave is independent of the medium. Okay. Oops. So you could have a light wave. It travels from the sun through outer space. It enters the atmosphere. It enters some water. It goes through some glass. It goes through the air again. It goes into your eyeball. For all those different mediums, the wavelength is changing, but the frequency stays consistent the entire time. Okay, so the frequency in a medium is equal to the frequency in a vacuum. Okay. So there you have it. So what are some typical indices of refraction? Index of refraction of water, I want to say is, don't quote me on this, but I want to say it's 1.3. Index of refraction of glass depends on the type of glass. Index of refraction even depends on the water. The salinity of the water affects the index of refraction. But for glass, I believe it's in the 1.5 to 1.7 range, depending on the type of glass. Things like diamond, I believe, has an index of refraction of 2 plus or more. So different materials, kind of like the more dense the material is, the larger the index of refraction goes. Okay? So there. So what I want to talk about now is what happens if we have a transition between materials. Okay. So here's a boundary between materials. Over on this side, we have an index of refraction N1, and here we have an index of refraction N2. All right, and there's and I'm going to draw a dashed line. This dashed line is the normal, or the also known as the perpendicular to that boundary. Okay. All right. So we have some light coming in. So here's the light that is coming in. So we will call this the incident light. It's the incident light. Okay, so when the light enters the, or when it hits the boundary, some of the light is going to be reflected. Okay, so, or I'm going to call this the incident beam, like it's a laser pointer or something. So this would be what is called the reflected beam. Okay. And then part of the light goes through. Okay. So this is called the refracted beam, also known as the transmitted beam. Okay. All right. So yeah, so basically the light splits into two parts when it hits a boundary. Okay. I know it's been a while. Well, I guess if you are, let's say you go outside your house, all right, and you stand in front of a window, you might be able to see your reflection in the window. Have you ever been standing in front of a window and you can see your own reflection? That would be the reflected beam, okay? But the person who is inside the building is still able to see you, right? So that person is seeing the refracted beam or the transmitted beam. Okay? Now, it kind of depends on the boundary, how much is transmitted and how much is reflected. All right? All right. So, these angles have some different names. Okay? So if we look at this angle right here between the incident beam and the normal, I'm going to call that theta 1. Theta 1. Okay. If we look at this angle right here, I'm going to call that theta 2. And then if we look at this angle right here, so the angles are defined with respect to the normal, okay? I'm going to call that theta 3. All right, and these have names. So theta 1 is called the angle of incidence. Theta 2 is called the angle of refraction. And theta 3 is called the angle of reflection. Okay? So there are these three different angles. So, and now I'm going to give you an equation that relates all these angles. So basically, let me go back to this page. The angle of incidence is kind of controlled by the experimenter. So maybe the experimenter has a laser pointer and they're choosing how do they aim the laser pointer at the interface. Okay, so that's controlling the angle of incidence. Okay, but then once the angle of incidence is set by the experimenter, physics determines the angle of refraction and the angle of reflection. Okay. Okay, so it turns out that theta 1 is going to be equal to theta 3. Okay, so what this says is that the angle of incidence equals the angle of reflection. So this is basically how mirrors work, okay? This is how mirrors work. Angle of incidence equals angle of reflection. And then to calculate the angle of refraction, we use what is called Snell's Law. And what it says is n1 sine of theta 1 equals n2 sine of theta 2. All right? So this allows you to calculate theta 2. You're going to have to do an inverse sine, as I'll show in a moment. But yeah. So this rule is called Snell's Law. Okay? So these are important equations. All right? Now here's something interesting. If we look at the angle of refraction, theta 2, rearranging Snell's law, we can see that n1 over n2 sine of theta 1 equals sine of theta 2. Okay? So we can see that how the light bends depends on not only where the light is entering, but where it's coming from. Okay? Oh gosh, excuse me. So this actually explains something kind of interesting, right? Have you ever opened your eyes underwater and it's all blurry? Why is it blurry if you open your eyes underwater? The reason is that normally, under normal circumstances, the light is coming from air into eyeball fluid. And that's what, okay, so you have N1 is air, the index of refraction of air, and N2 is eyeball fluid. I'll call it eyeball juice. Okay, and so that's what's happening in your Snell's law. Okay. All right. But if you're underwater and you open your eyes, N1 is not the index of refraction of air, it's the index of refraction of water. Okay? Which is different from air. And so you're going to get a different angle of refraction, which is going to impact where the light hits the back of your eyeball. So it messes it all up. Okay? So, so what that means is that your vision is all distorted because the light is hitting a different spot on the back of your eye. Okay? Now, you might notice that when you wear goggles, you can see just fine underwater. So why is wearing goggles allow you to see just fine? It's because if you look at the goggles, the space, your goggles have a pocket of air. And so the air is in front of your eye. And so, once again, we have an air to eyeball juice transition. Okay. Fishies, they already know about, if you took a fish and you took it out of water, a fish is not going to be able to see out of water because the fish's eye is evolved to see things properly in this water to eyeball juice transition. If you take it out, it's going to be an air to eyeball juice transition, so it's not going to be able to see. Okay. Let's talk about prisms. Why do prisms separate light? It's because these indices of refraction depend on wavelength. Okay, so what that means is that the angle of refraction depends on wavelength. So that means is that when you have some light that is entering a medium, so maybe this is white light. White light is a superposition of all the different colors. Then different wavelengths of light are going to have different indices of refraction, and so you get it separated out into a rainbow. Okay. We can talk about how lenses work. How does a lens work? And lenses work by having a curved interface. Okay, so the interface is curved. So maybe this side is glass and this side is air. All right. And so the light is coming in like this. So how do we apply Snell's law if you have a curved surface? Well, if we think about this beam of light, what you want to do is you want to define the tangent to the surface. Okay, so I would draw the tangent, and then I would draw the normal to that tangent, and then that is my angle of incidence. Okay, and then I use Snell's law to find the angle of refraction. This would be theta 2. And basically what this curved surface would have the effect of doing is taking the light and redirecting it like that. Okay. So glasses work by using Snell's law. Okay. So let's do an example. Okay. So let's suppose you have an interface. All right. So this is air. Okay. And this is glass. So we have light traveling from glass into air. Okay. And we'll say that this glass has an index of refraction of 1.5, and air has an index of refraction of approximately 1. Okay? Some light is incident with an angle of incidence equal to, let's say, 13 degrees. All right? Now, maybe you guys have done this before. Have you ever been in a pool with goggles on, and you go underwater, and you look up at the surface of the water, and it looks like a mirror, almost, okay? That's very similar to the fact that if you were inside this glass, and some light is going towards the edge of the glass, some of it is going to bounce right back, like a mirror. Okay, that's called the reflected beam, and the angle of reflection is going to be 13 degrees. Okay, so it's really easy to get the angle of reflection. Okay, some of the light is going to be refracted and transmitted into the air. Okay, to get that, we have to do Snell's law. So this is kind of the 1 side, and this is the 2 side. So we have N1 sine of theta 1 equals N2 sine of theta 2. All right. So N1 is the left-hand side, so I have 1.5 sine of 13 degrees. All right, equals N2, which is approximately 1 sine of theta 2. All right, so computing the left-hand side, I have 1.5 times sine of 13, and that gives me 0.337 equals sine of theta 2. Okay. And then I have to do what's called an arc sine or an inverse sine in order to get theta 2. If you don't know how to do arc sine or inverse sine on your calculator, please talk to me in the Zoom room session and I can show you how. And that gives that theta 2 is 19.7 degrees. Okay, so what that means, if we had an angle, if the light went straight through, then this angle right here would be 13 degrees. So this is greater than 13 degrees, right? So that means that it actually kind of bends away from the normal, like that, in this case. All right. So this right here would be 19.7 degrees. One of the things about the transmitted beam is that it always goes to the quadrant on the other side. Okay, so you might remember from your math class you have like the quadrants 1, 2, 3, 4. So the light is coming in the third quadrant. It's gonna the transmitted beam is always going to be in the first quadrant in that case. Okay, so it doesn't go to the adjacent quadrant, it goes to the opposite quadrant when it's transmitted. Okay. So we're almost done here. Let me ask you this. What is the largest possible theta 2? Type it into the chat if you know. What is the largest possible value that theta 2 could have in order to be considered as transmitted? Deleting emails as I'm waiting for a response. Very good. Yeah, 90 degrees. Okay. So 90 degrees is the largest possible, the limit. Okay, we'll say the limit. If you're in calculus, it's the limit. Okay, and the reason is that if it's more than 90 degrees, it's actually curling back into the previous medium. Okay. So the angle of incidence that results in theta 2 equals 90 degrees is called the critical angle. Okay. It's called the critical angle and denoted by theta c. All right. So let's redo that previous example and let's figure out. So we have here n equals 1.5 and here n is equal to 1. So what is the critical angle in this case? All right. So I have n1 sine of theta 1 equals n2 sine of theta 2. Okay. Now, theta 2 is 90 degrees. So I have, and then the index of refraction on this side is 1. So I have 1 equals 1 times sine of 90 degrees. And then on the left-hand side, I have an index of refraction of 1.5, and I have sine of the critical angle. Okay? Now, sine of 90 degrees is 1. So what I have is sine of theta c equals 1 over 1.5. Okay? All right. So doing the inverse sine of that, I get that the critical angle is 41.8 degrees. Okay? So what happens? So let's suppose that I'm going to draw another dashed line. So this dashed line right here is 41.8 degrees, the critical angle. Okay. Okay. If theta 1 exceeds the critical angle, there will be no transition or no transmission. No transmission. It will be all reflection. Okay. So here's the critical angle right here. So what if we had light coming in from a greater angle of incidence? Okay. So you have this angle is greater than 41.8 degrees. In that case, all of the light is going to be reflected. Okay. All of the light is going to be reflected and none of it will be transmitted. If you have a smaller angle of incidence, like this is less than the critical angle. In that case, some of the light is going to be transmitted. Okay? So one of the things I wanted to point out is that energy is conserved. Okay? So what if the energy in this incident beam is 100 joules? Okay? Then let's say that 30 joules are reflected. Okay? Then that means that the energy of the transmitted wave has to be 70 joules. You get what I'm saying? So you have to have conservation of energy. And how much of the light is reflected versus transmitted depends on the angle of incidence. So what happens is as the angle of incidence approaches the critical angle, the energy contained in the transmitted beam starts dropping to zero. Okay? And the reflected beam the energy in the reflected beam starts to grow. All right? One of the things you might notice, if I look at the phone, I wish I had a piece of glass, a clear piece of glass. You might notice that glass looks like a. So even if I turn this, well, that's not good. Come on. What I really wish I had is a flat piece of glass. All right. You know what? I have an idea. Give me 1 second. Okay. This isn't the best example, but I've got a baking dish here. Okay. And what we can see, all right, is there's light from my face that's going and hitting this this glass thingy, okay, this glass surface, but you can't see me here because very little of the light from my face that hits this is being reflected towards the camera, okay? But what if I make it a really steep angle of incidence? All right, let me see if I can. should. Oh, there I am. Look at that. See how you can start to see my reflection right here, okay? Whereas if I change the angle, you no longer are seeing my reflection. So that's because if I kind of am going like this, gotta get the angles right, the light from my face is exceeding the critical angle, and so none of it transmits over to the other side. It all reflects towards the camera, okay? That's why surfaces tend to appear glassy. If you're looking at them almost edge on, all of a sudden they'll appear glassy because you're exceeding the critical angle, okay? So anyways, that's my lesson for today, and I will